Okay, hello students. Today we'll start in our new chapter, chapter 14, Introduction to Normalization using Functional Dependencies. This chapter we will learn what do we mean by normalization and what are normalization rules and how to apply them on our relation schemas. First of all, we need to know why do we need normalization. For example, if we have two different designs for the same relations, student and advisor. In design 1 we have a student schema with 4 columns. The first column, student number, name, address, and the advisor number, and the student number is chosen as the primary key. For the advisor we have advisor number, name, the address of the advisor, and the department of this advisor, with advisor number as the primary key. However, in design 2 we have both in one schema named student advisor, and with columns that consist of all the columns above: student number, name, address, advisor number, advisor name, advisor address, and the department. We know by looking that design 1 is better than design 2 because it separates different entities into different relation schemas. So design 1 is better when compared with design 2. If you want to explain more why design 1 is better than design 2, then we need to perform insert operations, update operations, or delete operations on design 1 and design 2. Let's, for example, add a student in design 1. If we want to add a student in design 1, then all what we have to do is adding a student number, the name of the student, address, and the advisor number of the student. However, if we want to add it in design 2, then in addition for these columns, which is student number, name, address, and advisor number, we need to add advisor name and advisor address or the department, or we can put null on these columns. So in this way, when we add a student in design 2, we will have many nulls, we will have many null values in this design, which will take more storage space when compared with design 1. The same thing applies when we want to add advisor in design 2. For example, if I add an advisor in design 2, I will fill the advisor number, the advisor name, advisor address, and the department, and I am obliged to add a new student with each advisor added to the college or university, for example. So I am obliged to add a new student, so I want to add a student number here and a name and an address, or put nulls here, but the student number column must be filled. So we have some problems or some anomalies we call when I want to make insertion operations or update operations or deletion operation. So how to transform this one into this one? We can, by directly looking, we can separate them logically, or if the design is not simple for us, more complex, then we need to apply normalization rules in order to change our relation schema from design 2 to design 1. And this what we will learn in this chapter. We take insertion anomalies. For example, if we do update operations to see update problems. For example, if I want to update an advisor in design 2, okay, I have an advisor already filled in the database, and I want to, for example, update the address for this advisor number. Then I want to go for this column and update the advisor for all the rows or for all students that have this advisor advising them. So for example, if we have an advisor advising 10 students, then I want to go for the 10 students and update the advisor address for all of these 10 students, which is time consuming and more complex than doing so in design 1, which I want only to update the address column in the advisor relation, and by the advisor number which is already filled in the students for this advisor, they can all see the update or they can changes done for the advisor relation. So we have also update anomalies, as we see. Also we have deletion anomalies. For example, if I want to delete a student from design 2, then I need to delete the student information, including student number, name and address, also the information for his advisor. So you are thinking why design 1 is better than design 2 for these problems that we list before. So the first guideline, while designing a relation, we must design a relation schema so that it's easy to explain its meaning, like student, advisor, not complex one like student, advisor at the same time. So we need to separate our entities into separate ones. So do not combine attributes from multiple entity types and relationship types into a single relation like this one. So we have the update anomalies. As we see, we have insertion anomalies, we have deletion anomalies, and we have modification anomalies. Okay, the second guideline, when designing our relations, design the base relation schemas so that no insertion or deletion or modification anomalies occur. So we need to design the relation so that we avoid occurring of insertion, deletion or modification anomalies by separating entities into simple ones, and by separating the objects for each component into a different one. If any anomalies are present, note them clearly so that the programs that update the database will operate correctly. So we need to take care of the anomalies and note them clearly before programs later on encounter these errors and make speed performance may become slow, for example. Okay, another thing that we must take care in designing our relation is the null values. We should go away or escape from null values in tuples or rows as much as we can. So avoid placing attributes in base relation whose values may be null. So when you design a relation, you must go for each column and ask yourself whether the values for these columns may be null. If we have if you think that the values may take nulls in a high percentage, then we should separate this column with the primary key in a new schema or a new table, and and give this attribute for the column in the correct places. So if nulls are unavoidable, if you can't avoid nulls, make sure that they apply in exceptional cases. Only exceptional cases must take null values only, and do not apply to majority of tuples in the relation. So why do we should escape from null values? The problems with nulls are waste storage space, because they take high storage from our disk. So in nothing, it's only allocated for null value, and this null value have multiple interpretation. For example, not applicable value or not known. For example, if we have a student table and a column mark for this student, for example, if the mark is null, then you start thinking why this mark for this student is null. This is because, for example, the student was absent, or the mark is not applicable or not known for this column. So we should avoid null values as much as we can, because also null values create ambiguities with aggregate functions like the count and the average, because when you apply aggregate functions, as we see in previous chapters, the count aggregate function will count all the rows except the null values, also the average. For example, if we have students in a table, each one with his mark, then if we have a mark null and we apply an average aggregate function, then this null will not be considered in while computing the average for all of these students, which is wrong at some times. Also, null create ambiguities with the joins, because if we have to join one table with another table on a specific column, and some values for this column were nulls, then these rows will not be considered in the result of the join between these two tables. So an example of null values and why we should and how we should avoid them. For example, if we have only 10% of employees have phones, then if we have this schema or relation, employee with SSN, the name, and the office phone, then if 10% of the employees have phones, then this column will will only be 10% used, while 90% of the employees will have the office phone column as null value. So this is a poor design, because 90% of the last column values will be nulls. So how do we solve this problem? We should separate the column that may take null values into a separate relation. Here we name it phone, and put the primary key of the relation, which is SSN, with this office phone in the phone relation, so that, for example, if we have an employee with a specific SSN, this employee may have a phone, and if, for example, if we have an employee without an office phone, then it will not be written in the phone table or phone relation. So we'll continue in the next video talking about functional dependency. Thank you for watching, and good luck.